Hello, today I'd like to share with you our work on developing a soft multimodal sensor and especially looking into our force sensing analysis that we've carried out so far. In traditional open surgery, surgeons rely on palpation. It is used to locate and protect blood vessels and nerves, to work in areas where visual feedback is obscured, and to identify unhealthy tissue regions, including cancers. Robotic minimally invasive surgery has many advantages. It reduces the patient recovery time compared with open surgery, as it uses small incisions, and it increases tool dexterity and control intuitiveness compared with other forms of minimally invasive surgery. However, robotic surgery has no direct tactile feedback, as there is no link between the tools on the robot and the surgeon. Force sensing has been introduced to some surgical units. This has reduced the forces applied during surgery. Stiffness sensors, however, have not been integrated into any robotic surgical system. This means that the surgeon has no ability to palpate tissue stiffness. The aim of our research is to restore the surgeon's palpation abilities when working in robotic surgery. To do this, we are producing a soft-tipped multimodal sensor capable of sensing force, tissue stiffness, stiffness transition boundaries, and cardiovascular pulsing. We aim to do all this through the tracking of an air-pressurized elastomer membrane. This is the pressure modulated optical tracking or PMOT sensor that we have produced. It consists of a stiff outer housing with an elastomer membrane covered in tracking points, all of which are 3D printed together, into which is inserted pneumatic piping and a camera. The pneumatic piping is connected to a pressure regulator, which is used to control the device pressurization. The camera captures the location of tracking points. This is then fed to a computer which uses commands in the OpenCV library to calculate and record the position of the center of each tracking point. Here is the iteration of the PMOT sensor used in the experiments explained in this paper. At the front, you can see the elastomer membrane with tracking points. This is connected to a sensor housing, into which is fed the camera and the pneumatic piping. The camera is also held at its tip. As the pressure is increased, the sensor inflates. This sensor has been inflated to 9 kilopascals. As forces act on the sensor, it causes the tracking points to move. This allows us to measure the force by tracking the tracking points. Focusing on force sensing. This is traditionally achieved by tracking the displacement of a hard-tipped device with known stiffness interacting with an object. Several soft-tip force sensors have, however, been designed in order to decrease tissue damage. However, no soft-tip sensor has been produced that can adjust its range on demand, allowing it to adapt to use case scenarios. Through analyzing the force sensing abilities of our sensor, we hope to show experimentally that the PMOT sensor can function as a single axis force sensor, and that the range and sensitivity of the sensor can be adjusted by changing the internal pressure of the sensor. To analyze the force sensing abilities of the PMOT sensor, it was mounted opposite a force torque sensor on a linear rail. The PMOT sensor was inflated before the force torque sensor was moved in steps into full contact with the PMOT sensor and back. The force and tracking point locations were recorded 5 times at each step. The experiment repeated 6 times per pressure at 9, 13, and 17 kilopascals. Results show that the PMOT sensor can sense force accurately, and that the range and sensitivity of the sensor could be adjusted by changing the internal pressure. As the internal pressure of the sensor was increased, its range increased whilst its sensitivity decreased. Going forward, we're developing an algorithm for inline tuning of the sensor depending on the internal pressure. We're also analyzing the angled force sensing abilities of the PMOT sensor. Further, we will analyze the PMOT sensor's other sensing modalities before miniaturizing the sensor for use in robotic surgery. Thank you.